Good day, Math 30-1s. Today we are talking about Chapter 10's first two topics, 10.1 and 10.2, which both look at the sums and differences of functions and product and quotients of functions. So essentially we are taking two functions, which could be polynomials, they could be radicals, they could be exponential, they could be logarithmic, they could be sinusoidal, they could be rational, and we are simply putting them together in one of four operations today. So we're either looking at the sum, difference, product, and quotient of functions. And in function notation, it could look something like this: f of x plus g of x, which could be written as f plus g of x. The difference, similarly, is an f of x minus g of x, or f minus g of x. And essentially, we're just getting used to the notation here. F of x times g of x, noting a dot filled in, dot product, is a multiplication. F times g of x, or you may also even see, without a sign, an fg of x, implying as well a product. And lastly, a quotient, f of x divided by g of x, or f over g of x. Now what we're going to explore today is the concept of these four operations in mainly one of two forms, either from a graph or from an equation. And these are the two main ways that we represent functions in grade 12. The main ways. So we're going to be sketching from a graph, and so I will be providing two lines, perhaps some of the most simple functions I can, to get us comfortable with the notation. So we're going to start off with an upward sloping line, a downward sloping line, and an addition of these two functions and a subtraction of these two functions. So in the very first one, we have a new function under the name h of x, which is created by adding f of x and g of x, where f of x is one line and g of x is noted as the other. So what would happen if we created a new y value from the addition of two other y values? Well, let's do this. I'm going to pick some very specific x values and work towards the right and creating some new values on h of x. Let's start at the negative 4x value and simply add the two y values together from each function. On the function f of x, we've got a negative 3. On the function g of x, we have a negative 1. And if we add together, a positive 1. If we add together a negative 3 and a positive 1, we get a negative 2. Let's move to the right and try a new x value. When we look at x equals negative 3, we're going to add together negative 2, positive 0 makes negative 2. Negative 1 plus negative 1 makes negative 2. And you might imply there's a trend here, but we'll do one more just to see if it confirms it. The y value on f and the y value on g at x equals negative 1 is a negative 2 and a 0. Adds together to make a negative 2. And in fact, there is a trend that is trying to tell us that the new function h of x appears to be a horizontal line at y equals negative 2. And in fact, we can confirm this by generating an equation if we use our slope-intercept form to generate the two equations of the lines. So what we're doing is we're looking at the sum of f of x plus g of x, where f of x has a y-intercept of 1 and a slope of rise 1, run 1, rise 1, run 1, a slope of 1. So y-intercept of 1 and a slope of 1 means our equation is 1x plus 1. For our equation for g of x, we have a negative 1 slope, down 1 over 1, down 1 over 1, a slope of negative 1, and a y-intercept of negative 3. So slope of negative 1, x minus 3, and if we add these two equations together to generate our new equation for h of x, we have an x and a negative x cancel each other out, and a 1 plus a negative 3, which results in a negative 2, which confirms our implications that this does trend towards a negative 2y value infinitely. So you might take a moment and pause the video and try to do this yourself with a subtraction of f of x minus g of x, but I will caution you that you do need to be very, very careful as you are subtracting some negative values. So if we're looking at the function f to start, and then we're going to subtract the g of x. We're going to start always with y values on the upward trending line. I'll start at the same place, -4, and work my way to the right. We have a -3 plus a 1. -3 minus a 1 makes -4. We have a -2 subtract a 0 makes a -2. -1 subtract a -1 makes a 0. And this is where we do have to be very, very careful. Again, f first. So we have a 0 minus a -2 makes a 2. One more. A 1 subtract a -3 makes a 4. And it does seem to make an upward trending line that is slightly more steep than f. And if we were to try to make a nice smooth curve connecting all these dots, we have a nice collinear pattern. Just to confirm that this should be a more steeply increasing line, let's look at our equation for f of x subtracting a g of x. Our function f of x we still have listed on the left as x plus 1, and our g of x is still listed as a -x subtracted 3. And if we do distribute the negative into the bracket, we do end up with an x plus an x, which makes a 2x, and a 1 adding with a 3, which makes a 4. And I guess this makes sense with a y-intercept of 4 and a slope of 2. Rise 2, run across 1. Rise 2, run across 1. So we've created two different lines by adding or subtracting lines together. As we flip it over, let's explore a different operation. Under the heading of multiplying and dividing, we are going to be multiplying or examining the product of f of x and g of x. We are going to be using the same functions together just to keep things simple, but under the new name m of x, the product can be examined in a chart. Now the only reason I'm doing a chart for this one is for those that may have struggled on the previous page organizing it all in their head. There is a way of doing this on paper. So we're going to pull out the y values, and this time instead of doing the addition, subtraction, or product in our head, we're going to write down the y values one at a time. So for -4 as an x value, the f of x value is -3. When we plug in a -3, out comes a -2. And what we find is a trend which seems to be increasing the value by 1 every time. So we'll just continue the trend. For g of x, when we plug in a -4, a 1 comes out, and then a 0 comes out, and then a -1 comes out, and again another trend continues. This time we are decreasing our y values each time. For this question, we are determining m of x, the product of f of x and g of x, which means we are multiplying the y values. And this time, though, we have this organized very nicely as a product of two y values in a chart. So -3 times 1, -3. A 0, a 1, 0, -3, -8, and -15. What we've produced through organizing all of our values is a list of x values and y values on our function m of x, which is the product of two lines. What is the product of two lines going to look like? Well, let's plot these x, y values and see. At -4, we have a y value of -3. At -3, we have a y value of 0. At -2, we're at a 1. At a -1, we're at a 0. At a 0, we're at a -3. And at a 1, we're down to a -8. And the other points do not seem to want to fit. If we make our nice smooth curve, your impression is correct. This is making a bit of a parabola. If we were to go a little bit further to the left, it would be symmetrical, and we would see this -5, -8 value appear. It does make a parabola. Does that make sense, considering we are multiplying two lines together? Well, in examining the equations in the bottom left here, we can multiply the equation for f of x, x plus 1, the equation for g of x, which is negative x subtract 3, and without even multiplying them together, we could induce that these have an x and an x coming together to create an x squared, which of course implies a parabola. So far we've been exploring general trends, looking at all x values as we create the graph. What we are occasionally asked is to evaluate very specific x values, and the next part is intended to get us used to notation. So under the heading of evaluating, I gave us two functions and a graph just for reference, but what we're going to do is, using only the equations, determine the values of h of x equals f plus g of 1. I could also have asked for h of 1 equals f plus g of 1, which imply the same thing. We're plugging 1 into the function h. F plus g is the function h that we're plugging 1 into. So we are examining f of 1 plus g of 1, which is going to give us two outputs when we plug in 1. Using the equations, if I plug in a 1, we have a 0.5 times 1 plus 1, so that's a 0.5 plus 1, or 1.5. When we plug 1 into g, we have a 1 squared minus 1, which gives us a 0. Add those together, and you do have a value of 1.5. I guess this is confirmed if we plug in the value of 1 into the graph. A 0 comes out, and a 1.5 comes out. Add those y values together, and of course, you have a 1.5. So there are questions where you're provided only with an equation or only with a graph, and you are expected to use either or. Feel free to pause and give the last one a try, but for the equation m of x, we've got fg of 2. So if we were asked to evaluate f of 2 times g of 2, using the equations, we would plug 2 into the function f, which gives us a half times 2, or 1, plus 1. For g of 2, 2 squared minus 1 is a 4 minus 1, or a 3. And a 2 times a 3 does produce an output of 6. So in examining an input of 2, our outputs are a 2 and a 3, which both confirm that their product should be a 6. So far we've examined, on the front page, addition, subtraction. On this page we've already examined multiplication, and there's one operation that we are missing: division. Having completed chapter 9, which is rational functions, we have a little bit more skill that may be needed for this question. Accurately draw each function in their quotient for a new function h of x, which is created through a division of g over f, where f and g are provided. G divided by f. Be very careful. G is the 2x plus 6 on the top. F of x is on the bottom, the x squared plus x minus 6. This is a rational function because we have a polynomial on the top and a polynomial on the bottom, a linear over quadratic, which quite conveniently does factor into a 2 times an x plus 3 divided by an x plus 3 and an x minus 2. What you most likely noticed was there is an x plus 3 on the top and bottom, which implies because there is a factor top and bottom, there is a point of discontinuity. The function h of x will result in the shape of a 2 divided by an x minus 2 with the restriction due to the point of discontinuity at x equals negative 3. This is our overall shape. So what we have is a 2 divided by an x minus 2. Comparing this to our a over x minus h plus k standard form for a rational function, we can see that this is shifting 2 to the right, there is no vertical shift, and there is a vertical stretch by a factor of 2. So as we draw our rational function shape, we are shifting our vertical asymptote 2 to the right. We are not shifting our horizontal asymptote up or down anywhere, but we are drawing our shape with a vertical stretch by a factor of 2. So typically, in the shape 1 over x, we are saying from our new origin, 1 to the right should be 1 divided by 1 is 1. But we're vertically stretching up times 2. So now we are 2 up from where we're vertically stretched by 2 from where we're supposed to be. Normally, if we go 2 to the right, we are a half up, but we're vertically stretching by 2 to go a full 1 value up. A half to the right, 1 divided by half puts us at a 2, but vertically stretching up to a 4. And there's enough room to sketch the trend. In the bottom left, same pattern, coming from our great knowledge of 1 over x, is 1 to the left should be 1 down, vertically stretching down to negative 2. 2 to the left should be a half down, vertically stretching times 2 puts us there. 3 left should be at a third, but stretching to 2/3 down. 4 to the left should be a quarter down, but stretching to a half down. And one more point in the middle here. A half to the left should put us down negative 2, but stretching down to negative 4, and there's enough of a trend. Two very important questions come out of this: domain and the range. Now, I did not talk about one specific part of this as I sketched the shape of this graph. I haven't commented yet about that point of discontinuity that's been lurking there the whole time. There is a point of discontinuity at x equals negative 3. So I do need to sketch a hole at x equals negative 3. This part of the graph does not exist. So as we ask the question, what is the domain? We can say that the x values are such that x cannot be negative 3, point of discontinuity. 2 is an asymptote, but x can be everything else. X is an element of the real number system. Nothing too crazy with that because we focus quite heavily on x. The range is a little bit trickier. Most people would look at your y values and say, well, there's your asymptote, y cannot be 0. Y is such that y cannot be 0, but there's one that is forgotten. We've already stated that x could not be negative 3, which means there's actually a y value attached to that point of discontinuity where our graph does not exist. How do we determine a y value from an x value? Well, we conveniently have an equation above which says the y value is based on x. So the y value that contributes to our restricted range comes from y is equal to 2 divided by x subtract 2. And what is our x value? Negative 3. So 2 divided by a negative 5 gives us a negative 2/5 restriction to complete our range. So y is such that y cannot be 0, negative 2/5, but it could be everything else. And there's your completed range. The last part of our lesson comes from restrictions. For f of x equals square root of x minus 1 and g of x is x minus 2, first part, determine the equation of a new function h of x, which is f divided by g. So we are talking about some function f divided by some function g, where f is the square root of x minus 1 and g of x is linear x minus 2. Noting now that we're not limited to polynomials and rational functions. In chapter 10, our function operations allow us to talk about radicals, polynomials, sinusoidal functions, exponential functions, logarithmic functions, as well as rational functions. We can deal with any combination of functions discussed in 30-1, including absolute value functions and piecewise functions as well. So, before moving on to part B, I do want to jump down to the domain and ask, what is our restricted domain? Knowing full well that in all of math there are two main places where restrictions come from. Radicals, you can't deal with a square root or fourth root or sixth root or an even root where there's a negative under the radical sign. So I might state that that inside of the radical, x minus 1, needs to be 0 or more. there's an important piece. We also have another place where restrictions can occur in math, and that is in denominators. The x minus 2 on the bottom, that is not allowed to be a 0. So we have x has to be greater than or equal to 1, and we have x cannot be a 2. Piecing this together, you could visualize this on a number line and say everything to the right of 1 is okay, including 1. But I'm going to pause for a moment. 2 we said was not okay. So I'm going to put an open circle to say 2 is not okay, but everything after that is okay, and imply that arrow continues to the right. In our notation for domain, we can say x is such that x has to be greater than or equal to 1, except it cannot be 2, but it can be everything else. And notice that I'm saying separated by commas the 3 different parts that contribute to our completed domain. In function operations, we are dealing with addition, subtraction, multiplication, and division through graphs and through equations of any functions so far.